Our next speaker is Dr. Michael Ashley. He leads product development at Metique, the clean chemistry company, as it builds and delivers electrochemical solutions to market. Michael has a PhD in chemical engineering from Northwestern University. He combines backgrounds in R&D and project development to drive Metique's low-carbon electrochemical process to commercialization. His talk title is Electrochemistry for the Profitable Decarbonization of Chemicals. Michael, take it away.
All right. Thank you, John. Appreciate that. And thanks to Aaron as well for helping get everything set up. So I will just share my screen here. And also, really interesting talk. And thank you, Patrick, as well. There's some aspects of this talk that I think you'll find interesting. And I know our lead data scientist would be very interested in speaking with you. But we'll get there. And thanks again, John, for the introduction here. So as John said, my name is Mike Ashley. My contact information is here, so please feel free to reach out to me if you want to follow up on anything that I'll be discussing. And I will jump right in with that. So the quick agenda that I'd like to go through here before we jump in is just that we'll be talking a lot about the chemical sector today, and specifically about electrochemistry. And we'll get into why chemicals are a key pillar of decarbonization moving forward, but then also talk about how electrochemistry is a very versatile technology suite that will allow us to decarbonize many of the chemical products that power our world today. So really, the industry has rallied around green hydrogen, and certainly this is the best known or most publicized example of industrial electrochemistry today. So splitting water electrochemically into oxygen and hydrogen. And of course, this has gained quite a bit of attention over the past couple of years. So we'll start by talking about green hydrogen, some work that Metique has done in the green hydrogen space. But then I'll use that really as a benchmark to talk about how we should think about economics of electrochemical processes as we seek to profitably decarbonize the production of chemicals. And specifically, what you'll hear me say probably 4 or 5 times throughout this talk is that electrolysis can do so much more than just produce green hydrogen. That would really be the key takeaway from my talk today. So I'll use that to transition then into 2 case studies of industrial electrochemistry for applications beyond hydrogen production. And specifically, I'll talk about ethanol oxidation to acetic acid and phenol hydrogenation to cyclohexanol. So these are things that can be done electrochemically using a very similar technology stack as the electrolyzers used today to make green hydrogen. And finally, I'll wrap up with a brief discussion about how we aim to get to industrial deployment, and specifically, what are the performance metrics we need to hit for these processes to be economically viable. So very briefly, I'd like to introduce the concept of hard-to-abate sectors, and specifically how industry could become the biggest U.S. climate problem in a decade. So this data is adapted from some great work that the Rhodium Group did last year, and it really makes one key point. If we look at industry, which is mainly comprised of cement, steel, and chemicals, we can quickly look and see that if we take today's U.S. carbon emissions broken down by sector, you can see that transportation is the biggest emitter, followed by industry and power generation in approximately a tie for second place. But if we fast forward to 2035, the key differences here are that transportation and power generation, more acutely, we expect to undergo significant declines in the percentage of carbon emissions that they make up throughout the United States. This is due to economically attractive use cases today, such as wind, solar, batteries are starting to take over the electric grid, and transportation is increasingly being electrified, especially with passenger ground transportation. However, in a business as usual scenario, we don't see any change in industrial emissions, and that is primarily because today there are no economically attractive solutions that can take over and decarbonize cement, steel, and chemicals. And so today I'll be focusing specifically on chemicals here. And our core thesis as a company is that electrochemistry is key to eliminating the emissions associated with the chemical sector. It won't solve every decarbonization challenge in the industry, but electrochemistry is a very versatile technology suite that can address many, many chemical processes and decarbonize them as, like I said, we have an increasingly clean electric grid. So our vision is to leverage electrochemistry to accelerate the transition of the chemicals industry, which today is powered by fossil fuel feedstocks and fossil fuel heat, into one powered by renewable feedstocks and electricity. And as I will continue to say, the investment in water electrolysis is going to accelerate our path there. We can leverage that same technology suite to build on top of all the gains that we've had from the R&D, manufacturing, deployment, operation of green hydrogen plants, and use that same technology suite to decarbonize many, many other chemical processes to produce the chemicals, fuels, and plastics that power the world. So I'll quickly start with a discussion of the green hydrogen space and then transition into a few other application spaces. And specifically, one challenge that Metique has addressed is that while the industry is rallying around green hydrogen as a decarbonization tool, PEM electrolysis, which is emerging as a specific application or really rather technology type within the electrolysis ecosystem, suffers from a notable materials challenge. And those of you who have followed this industry have probably heard that iridium, the use of iridium as a key electrocatalyst material within PEM electrolyzers, is starting to pose a significant challenge, both from a cost and supply chain perspective, in the manufacture of PEM electrolyzers at scale. So quickly, I'll direct you to the left-hand side of the screen here. So this is iridium production today, or rather last year. The iridium production across the globe is basically flat at 7.5 tons per year. The reason this is because iridium is actually not produced on its own. There are no dedicated mines to produce iridium by itself. Rather, it's a byproduct of platinum refining. And as a result of that, it's expected that the total iridium production in the world remains relatively constant around this 7.5 ton per year mark. And at a price point of about $5,000 an ounce, that is quite expensive. This leads to a fairly sizable market size for iridium as a whole. But what is coming is imminent market disruption led by the deployment of PEM electrolyzers at scale. Market forecasts predict about 100 gigawatts of PEM electrolyzer deployment by 2030. And to deploy this many PEM electrolyzers would lead to a significant mismatch in the amount of iridium that would be needed to supply that amount of electrolyzers and the amount that will be available for this specific application. And so we illustrate that difference on this right bar chart, where this light blue color is the forecasted demand that will come online by 2030 with PEM electrolysis. And so we see that there's a significant mismatch between demand and supply that is coming later this decade. And so we can ask the question then, why is iridium so good for this application, and why can't we just substitute in a different material? And the answer to that is that iridium is uniquely good at PEM electrolysis. That is, it's the anode catalyst, it splits the water in the initial step in the process, and it is uniquely durable in the strongly acidic and highly oxidative environments that you see in PEM electrolyzers. So substituting a new material for iridium has proven quite challenging over the previous decades. And so really this is where Metique has deployed its technology suite. And really our objective has been to identify and industrially qualify materials that can substitute for iridium oxide in PEM electrolyzers. And so I'll quickly walk through how we have addressed this problem and our ongoing work in this space. So we have developed and deployed a high throughput experimentation technology that allows us to very rapidly synthesize in the physical world and then screen for properties combinations of materials. Rather, that is arbitrary but controllable bi- and trimetallic catalyst materials. So think alloys of materials that we can blend together in arbitrary but controlled ratios in order to reduce the amount of iridium that is needed for PEM electrolysis catalysts. And at the top of my talk, when I said Patrick might be interested in part of the discussion here, this is what I was referring to. What we were able to do in a period of just about 6 weeks is characterize, again, in the physical world, over 1 million material combinations and screen their properties for PEM anode catalysis. We were able to do this in a very short period of time. And the key part here in terms of data collection is that we were able to screen these materials under highly controlled and highly reproducible conditions. So we are able to generate very, very large data sets characterizing these materials systematically. What we were able to then do is filter out. So effectively what you're looking at in this plot is the trimetallic phase diagrams of the quality of these alloy catalyst materials relative to a benchmark iridium oxide, where orange is good and black is bad. And effectively then what we did is filtered out what we characterized to perform at least as well as iridium oxide, both from a activity and durability standpoint. And those are the dots you're seeing on this plot on the bottom left. So we've identified a portfolio of materials that via our high throughput experiments, we've identified to be very good at PEM anode catalysis. What we then did is started to scale these materials up and integrate them into real electrolyzers such that we could test them in scaled up conditions over real world operating conditions over long periods of time. And so we've been able to successfully qualify more than one material now from this portfolio that has comparable degradation rates as iridium oxide, but over a 2/3 reduction in the amount of iridium needed to drive that process. So effectively, what we've been able to do is qualify materials that give us an over 50% materials cost reduction with no loss in performance. And so we're validating these materials now at larger scales with our catalyst manufacturing partners, but are very excited about the work we've done here. And finally, if we really think about what we've done here, it is the validation of low iridium oxidation catalysts for their durability in industrially relevant electrolysis conditions. And so while this is very useful for PEM electrolysis, there are other things that this suite of materials can be used for in industry. And so there's, like I mentioned on the previous slide, some incumbent electrochemical applications like electrowinning, electroplating, wastewater purification. But this also sets the stage for the use of low iridium catalysts in other electrocatalytic processes as well. And that's what I'll be getting into for the rest of the talk. So for example, not only is this material set good for PEM electrolysis, but also for other oxidations. So things like ethanol oxidation instead of water oxidation. And so before we get there, I'd just quickly like to talk about how we think about the economics of electrolysis systems as a whole. So on the left here, I'm showing you a scheme of how a PEM electrolyzer looks. You feed in water, you split that water at the anode and evolve hydrogen then at the cathode. However, as a lot of folks in this space have now crunched the numbers and realized, of course, this has a very significant electricity requirement in order to produce 1 unit of hydrogen. And in round numbers, we're working at about 50 kilowatt hours per kilogram of hydrogen input to output ratio. And so if we then look at the numbers and say, all right, let's take a reasonable industrial electricity price, say in the US Midwest, we take this electricity requirement of 50 kilowatt hours per kilogram, and if you just multiply those numbers together, you can see that the electricity cost alone per unit output of hydrogen is about $2.75. When you layer in the rest of the costs needed to get this hydrogen out, call it your balance of plant, your CapEx, your other operating costs, compression costs, for example, you get to a total levelized cost of that green hydrogen production of about $4.50 per kilogram today. And so you can compare that then in round numbers to the existing levelized cost of fossil fuel produced hydrogen from steam methane reforming. And again, in round numbers, you see about $1.50 per kilogram to produce what is known as gray hydrogen. And so again, just for simple analysis here, what we then see is the Inflation Reduction Act with some very generous incentives that will have jump-started this industry, and it's quite exciting. But the quick math shows you that $3 per kilogram maximum incentive for green hydrogen production from the IRA is effectively meant to cover the spread between the levelized costs of green hydrogen and fossil-produced hydrogen. And so the reason, though, that I've put these couple in different colors is that you can see, based on this very basic economic math, that the electricity that you need to power this process is actually significantly above the levelized cost of the existing production method of fossil hydrogen. And so that remains a challenge. And there's some great companies out there working to reduce the cost, the levelized cost of green hydrogen. But this remains a fundamental challenge for the industry: is how do we make these numbers work while also ensuring that we are using truly clean power to drive this process? But given the fact that economic returns will drive scale in this space, are there other more economically attractive electrochemical applications we should be dedicating resources to? So green hydrogen represents an outstanding decarbonization opportunity, but can we direct some of our other efforts in development and deployment towards other applications in electrochemistry? So again, I'll come back to this point that there are so many more things that we can do with electrolyzers than just make hydrogen, and I really want to drive this point home. On the right-hand side of the screen here are all the functional group transformations that have been reasonably demonstrated to work. These are the other application spaces that we can look to as we evaluate other attractive applications in electrochemistry. And as you can see, there's quite a few applications we can think about. So given this universe, how do we then narrow down towards the most attractive applications in electrochemistry that we should go to next? We look at three main buckets to qualify these applications. First is economic. So looking at profitability without incentives, that's the key place to start in terms of this economic analysis. The market size of those products as well. And then a technical analysis. How difficult is this reaction to develop and then deploy at scale? And finally, looking at the competitive landscape for these different application spaces as well. And what I mean by that is, what unique operational benefits does electrochemistry afford that you wouldn't be able to get from the conventional thermal processes that drive them today? So can we unlock new chemistries that allow us to avoid the use of harsh chemical reagents like cyanide, bleach, nitric acid? Can we unlock a new chemical pathway to avoid explosive intermediates like ethylene oxide? So these are the types of other competitive advantages we seek when evaluating electrochemical applications as well. And finally, of course, the life cycle analysis and environmental benefit is a key role in the decision-making process as well. So I want to come back then to the economics and the electricity demand of various electrochemical processes. The scheme on the left is what you just saw a few slides ago, where again, we have a 50 kilowatt hour per kilogram need to produce green hydrogen. And I'll emphasize here that your typical green hydrogen system will operate somewhere around 1.8 volts. And that's going to be important in a moment. If we then look to another possible application in electrolysis, say feeding in ethanol instead of just water on the anode side, what we can do is a few things. One is we can develop a value-add chemical transformation at the anode instead of producing oxygen at the anode, which is typically just vented, not always. But we can do this value-add transformation from ethanol to acetic acid, which is a large market platform chemical, very valuable across a range of applications. And what we can also do is then still evolve hydrogen at the cathode. And so this is a similar electrochemical system as a conventional water electrolyzer, but what we've gained is a value-add transformation at the anode, as well as the ability to operate at a lower voltage than a conventional water electrolyzer. The reason for this is that it's easier to oxidize ethanol than it is to oxidize water. And as a result of that, we can cut our operating voltage about in half. And as a result, cut our electricity requirement in half. And so the result of this is a few things. With that same 50 kilowatt hours that we needed to make 1 kilogram of hydrogen in the base case, we can now make 2 kilograms of hydrogen because we reduced that voltage twofold. And we can also produce a much larger quantity of acetic acid. And this has to do with a few things, but primarily it has to do with the molecular weight of this material. The fact that you just need fewer electrons to drive a transformation. So I'm happy to get into more details on this if anybody would like to hear more. But we see this as a very economically attractive prospect, where just intuitively you can see that 50 kilowatt hours goes much further with this application than it does in conventional water electrolysis. So I will move then along to a second case study, which is also related to the hydrogen space. And this first scheme on the left is, again, your conventional green hydrogen electrolysis, followed by a second thermal hydrogenation step. So it's, of course, always critical to think about, all right, we're making green hydrogen, but what are we going to do with that hydrogen after the fact? And so this is a typical conventional type of hydrogenation where what we need to do is feed in hydrogen at elevated temperature and pressure, hydrogenate something like an aromatic ring. And so what I'm proposing is that instead of this emerging pathway of first making green hydrogen and then having a second dedicated step towards that hydrogenation, this requires dedicated hydrogen infrastructure, so compression and storage of hydrogen, followed by a second conventional thermal hydrogenation reactor. What we can instead do is integrate this all into one process using electrochemistry. And specifically here, what we're looking at on the right scheme is a direct electrochemical hydrogenation of phenol to cyclohexanol, where at the anode in this electrolyzer system, we're doing the conventional oxygen evolution reaction. What this does is generates protons in situ, and instead of evolving hydrogen at the cathode, what we can do is hydrogenate phenol in that same reactor. And so this gives us many operational benefits, but most concisely, it circumvents the need for dedicated hydrogen infrastructure. And you don't need that hydrogen storage, compression, and subsequent thermal reaction to produce your hydrogenated product. Okay. With that, I will wrap up with just one more slide, and then I'd be happy to take questions after that. The point I'd like to leave you with is, in addition to just saying that, again, electrochemistry can do so much more than just produce hydrogen, we can, with very achievable performance metrics, drive these other applications to commercial viability. Based on some of the take-home points from those two case studies, intuitively, you can see how they would lead you to better economic prospects. And really what I'd like to say here is that with modest performance targets, we can start to approach commercial viability of these other clean chemical processes. So just to give you a sense of what I mean by that, in terms of current density, where with hydrogen, we want to get to at least 3 amps per centimeter squared. With the ethanol oxidation reaction, we can target much more modest performance metrics, say 0.8 amps per centimeter squared, and still hit commercial viability. Similarly, on selectivity, of course, again, in the hydrogen case, your selectivity to hydrogen is near 100%. That won't be the case for all electrochemical reactions where you have competing pathways. So in the ethanol case, for example, you have acetaldehyde as a potential byproduct along with acetic acid. And so if we can hit a 80% or more selectivity to acetic acid, the numbers start to look very good. And finally, a stack lifetime. Durability is king in this space. Can we design systems that can withhold these electrochemical conditions or withstand these electrochemical conditions for long periods of time in the field? And so really, this is a key part of the puzzle moving forward, is designing systems, not just the catalyst, but the entire electrochemical system that can survive for years of operation. And so this is a key driver of the economics and something that we are very focused on. But again, we don't need to hit the same performance targets as we're seeing in the hydrogen space for the economics of these processes to look attractive. So with that, I will pause for questions. And again, I am very happy to discuss these economics and performance targets in more detail, perhaps on any follow-up meetings that folks here would like to have. But again, my contact information is here. So please feel free to reach out anytime. And again, I will also be at the roundtable a little later this afternoon. So thank you again.
Great. Thanks, Michael. We have one question. It's wonder what this does to minimize efficient scale of production. It would seem one could deploy smaller, more efficient production unit ops closer to need, scale to that specific need, unlike today's massive chemical plants that work on scale and centralization. Have you guys put any thought into that?
Yeah, we sure have. So the modularity aspect really opens a lot of doors, as the question suggests, for distributed chemical production. And so you can develop and deploy right-sized reactors at or near the point of use to dramatically reduce or eliminate transportation or supply chain costs. And so there are some really attractive examples of this, but effectively, you know, as the question says, what we can do is phase in the investment and say, all right, we don't need a massive, 100,000 or 100 kiloton a year plant for the economies of scale to kick in and for the economics to make sense. We can be efficient at smaller scales, and so we can deliver then chemical products to the point of use in an economically attractive way. So yes, absolutely, right. It's a great question.
Yeah, that sounds like a very interesting future industrial kind of approach to things. So yeah. All right, let me see if anything else has come in. I think we're good. Really appreciate the talk. Looking forward to the roundtable.
Outstanding. Thank you very much.
All right.
Appreciate it.
Thank you.